Hi
Hello, sir.
everyone.
What?
Yeah, am I audible?
Yes, sir. Yes, sir.
Yeah. So, do you have some doubt?
No, sir. I just wanted to ask uh, exactly what is the plan for today? I mean,
Okay.
how are we going to? Mm.
So yeah. So today we will go first through like some course summary, like in this week what we have covered. Okay, and after that we will go through some questions as usual, like our previous classes.
Sir, there is still some time to other people to join. No? So before that, can you give me a little bit assignment part B, this week assignment?
No. The
So
point is, yeah. The point is that please do not ask the current week
no, sir.
assignment questions. Okay.
No, sir. I'm
Okay.
just having a doubt. Like
Okay.
he is asking rigorous calculation with RADFRAC model, he is asked. So in
Okay.
the lecture, I have seen that professor is replacing DSTW model with distill and all.
Mm-hmm.
So here also will be following the same kind of procedure, or I am not sure. That's why.
Yeah, because I think they followed that procedure because when you want to do the rigorous calculation, first you need to have an estimation. So to get an estimation, first they choose this column. I think the distal one, and after that they went to the rigorous.
Sir, I'm having doubt in question 10 also. I think the way question 10 is done, um, the viscosity of the distillate in CP, like that he is asking.
Actually, I have not seen the questions, and the point is that suppose if you are having doubt, so maybe after this class, because in this class also we are going to have some discussion about questions. Okay, so maybe that will clear your doubt, or you can go through once again through the videos, or maybe then if still it's not clear, then after due date you can email me the question, and then I
No,
will
sir, I
email you
feel that
the
the question itself is not clear. 10th question.
Okay, so actually I don't have the assignment with me. So
Okay,
if
sir.
question is not clear, so just wait for the due date. Maybe if suppose if there is something, maybe let's say if there is something confusion in the question, so you can raise a query to the NPTEL team that this question I think it's not clear. So they will respond to you. Yeah.
Okay, sir. Understood, sir.
Yeah. Okay, so just wait for 2-3 more minutes. So after that we will start. Okay. So, good evening, everyone. I welcome you all to the live session for this NPTEL course Aspen Plus. So, the course instructor for this course is Professor Prabir Kumar Shah, and I am this course TA Amit Kumar Sharma. So as you all know, every week, every Sunday, we have a live session from 7 to 9 p.m. So in this live session, first we go through the previous week's course content, like the summary. And after that, we go through some assignment questions, previous year's assignment question or some basic questions, okay? And maybe regarding your doubts also regarding the previous assignments. So we will go through the questions and I will show you how to solve the question, and you can also raise your queries throughout the session. So it's like an interactive session. So it's good if you raise some queries also so we can have a discussion. And the recording of the session and the PPT will be shared to you from the NPTEL team. So those who are not able to attend today, they can have a they can access the PPT and video, okay, later. So let's start with the today's session. And I hope everyone is having Aspen Plus in their systems. So please open that Aspen Plus because we are going to solve some questions and you need that. Anybody have any doubt?
Sir,
Okay,
can you
let's start.
repeat what you just said?
Yeah, so I was telling that please open your Aspen also in the system in your computer because today in today's class we are going to solve some questions, so it will be very helpful for you. Okay. Okay. So in previous week, we have covered some case studies. Okay. So I think we have covered three case studies, different case studies. So the first case study was regarding the separation of hydrocarbon mixture. So this is the case study. So you have a hydrocarbon mixture. You have given composition, then you have given the flow rate, the temperature, pressure, okay, and you have given some conditions and like the mixture is to be flushed adiabatically with no pressure drop. So you have given a constraint also and conditions. The liquid line is the main product. Okay, so in this way you have given some instruction for your complete flow sheet. So whenever you want to model this complete system in the Aspen, so as we have already discussed, first define the components, then choose the appropriate method, then as the question say, follow that direction only, and in that way you will be able to complete the flow sheet and you will be able to you will be able to find the required solutions. Okay, so this was the first case study, and the objective was to verify the purity of each stream. So these were the objective, like model flow rate of the plant, volumetric flow rate, mass flow rate, heat duty of flash, composition of all the product line, and how much hexane is being lost in the stack. So this complete case study was covered in the class. So for the more detail, you can refer to the class notes also. And if the time permits, we will go through this case study after the discussion with the assignment questions. And the another case study was covered is the synthesis of acetaldehyde from ethanol. So in this you can see you have given the flow rates like same the temperature and pressure, and it is related to the isothermal plug flow reactor. Okay, so you've given data regarding the reactor, you've given the reaction kinetics also. So it's important because when you have to enter the reaction kinetics, then you need to be careful. Okay, because here it's mentioned that the temperature in the degree centigrade. Okay, so whenever you put these equations in the Aspen, so be careful with these conditions like the what is the temperature in degree or Kelvin. Okay, and also you need to see these values. So I think when you will enter the reaction kinetics in the Aspen, so in the Aspen you can see they have mentioned a standard formula. Okay, so compare this formula with the formula that have written in the Aspen, and based on that only you need to select the values of these constants in the Aspen actually. Okay, compare with this formula and then only the appropriate value should be entered in the Aspen reaction kinetics. Okay. If your reaction kinetics is not correct in the Aspen, then you will not get the correct results. It's very important to enter the reactions kinetics very carefully. So this was covered in the class. So for more detail, you can refer to the class notes. So for this the previous case studies, like it is mentioned that PSRK property method will be used. Then you have given the feed pump, okay, efficiencies, and regarding the reactor, so you have given some conditions for that. So it was given to you. The next case study was regarding the BTX separation through distillation. In this, you have given a mixture of benzene, toluene, and xylene, and you have given the temperature, pressure, then needs to be separated. So you need to separate them via the distillation with minimum purity of 95% of benzene. You have given some data regarding like you have to separate them with these constraints. So the purity of benzene should be 95%. The purity of toluene should be 97%. Okay, you have given the downstream pressure of benzene, toluene, and xylene. Okay, so you have given these conditions also. Then you have given a strategy. So you need to follow this strategy. Okay, so first verify the boiling point of each component. Okay, then you will identify the physical property methods, pure component and PT envelope. You can verify the K values to find the which one is the light and heavy keys. Okay, and then find the minimum reflux ratio and minimum number of stages using ASTW model, and then optimize IR stages and simulate real condition using digital block. So this is the strategy given in the question. So, so these are the case studies. So you have given the strategies already. But when you will model the system, the real system, or like maybe if you are in a company or in a project, then you have to develop your own strategy based on your experience, based on your like previous experience with that particular model or that particular system. So you can have your own strategies. But these are for your practice. So you can follow this strategy. Based on this, you will get to know so many things and you will be able to find out the solution. So these three case studies were covered in the previous week course. And now we will start with the questions. And after the questions, we will go through even strategy. So please open your Aspen also. And I think in some problems you will need your Aspen and others you can directly answer. So the question number 1 is, which among the following property method was used in the exercise of separation of hydrocarbon mixture in lecture 21? So it means to say that in this case study, we are talking about the separation of hydrocarbon mixture. So you have given some composition. So the question is asking about which method the professor or like in the class used for this particular case study. Or you can see the components also. So which method we should use? So which method will be appropriate for these components? The question is that. So it's regarding the hydrocarbon mixture and the separation. So you have options like Grayson, NRTL, Peng Robinson, and Uniquac. So take 2 minutes and let me know the answer. So we have two answers. I think the one is Peng Robinson, right? So we have one answer as C, Peng Robinson. And what is the reasoning behind this? So
It's a petrochemical industry.
yeah, please one at a time. Vamsi, please. Yeah.
Sir, it's related to petrochemical industry since we are separating hydrocarbon mixture. So
Okay.
PSRK method is discussed by the professor. So I think it is Peng Robinson.
Okay.
That's
And
right.
just suppose, so actually this question is the direct that was discussed in the class. But suppose if you are not aware that which method you have to choose, and what will you do then?
Sir, it is a gas mixture, so NRTL we can't use because NRTL method used for two liquid mixture. So
Okay.
from this like concept, we can choose Ping Robinson, like because
Okay.
it is a gas mixture.
Okay. Suppose who are not aware of these methods. Okay. So what do you think? Suppose if I'm not aware which method I have to use, then what is the tool available in the Aspen that I can use
Method
to identify the
assistant,
correct method? Okay.
method
So yeah.
assistant.
So in the Aspen, we have a method assistant. You can use that. So if you're not confident that which method you have to use, then you can use the method assistant that will ask you some questions. Okay, you need to answer that, and the questions are very simple. Will be like the basic question, like what are the components, what type of the components, what is the process. So you will know them for sure if you are having some kind of problem in your mind. So if you use that method assistant, then the Aspen will suggest you some methods. Okay, so these methods are the options for your particular problem. Then you can also take the help of the Aspen, and in the Aspen help documents you can find more detail about the methods, and you can choose the appropriate method. So for this, so it's about the hydrocarbon, and for hydrocarbon the Penck Robinson is the best method. And for the more detail regarding this, you can refer the class note, you can refer the Aspen help documents. The answer is Penck Robinson. So next question. So it's a figure 6 is the process to be simulated, and the figure 8 and 10, figure 8, 9, 10. So after this, there are some incomplete data input pellets, which upon completion would yield the same result are shown in figure 7. So answer the following question. So just quickly, you can just see a figure, this one. So then you can see there is a stream S1, then it's connected to the block B1. Then block B1, you have two streams S2, S5, then S2 is going through another component, another block B4. B4, then two streams S3 and S4. S5 stream is going to a heater or cooler, we don't know yet because we don't know the what are the results for these streams, so we cannot say about anything this. Okay, it's just a block. It's block B2, then it's going to a valve, it's block B3. So these are the stream numbers. So we have a question, the missing in value indicated by A in figure 8. So let's see the what is the figure 8. So this is the figure 7, okay, and this is the figure 8. So the pressure, it's asking about the value A, okay. So see this figure 8 very carefully. Just take 1 minute, 1 or 2 minutes, see it very carefully. Then I will go back to the other figures and let me know the answer. Have you seen it clearly? Can I move to the other figures? Everybody?
Yes, sir.
Okay, so you have seen it. Okay. So you are asked, so you have asked about the this A, the pressure. Okay. So these are the data. This is the figure. Again, you can see here. Okay. And can also look at it like this is the block B1, B4, B2, and these are the results. So now Observe it and let me know the answer.
Sir, 2, sir. 2 bar.
2 bar. Okay, so we have one answer, 2 bar.
Two bar.
So we have two answers now. So you can see the question again. Anybody wants to see it again? So this is the question. So you have asked about the value A. Okay. So this is the figure. Okay. And these are the values. And we have two answers, 2 bar. Anybody else?
2 bar.
So the missing value indicated by A in figure 8 is space or space. So there are two options. So you have only told me only one answer, 2 bar. What should be the next answer? Because
The next is the heat duty.
next is the
Heat duty.
no, not about heat duty. That is the B for A.
Okay.
It's for
Huh.
A you can use two answers. So you can use like you can put two values in the instead of like in the pressure and you will get the same results. So what are those two values? So one value you all agree is 2. What will be the other value?
0.
Zero.
Okay. So please tell me the reasoning behind 0.
So there is no
Pressure
pressure
drop,
change.
sir.
So the
Pressure
heat
drop 0.
duty is 0.
Okay. So the correct answers are 0 and 2. So whenever you have these types of question, first identify the blocks. So this is the block B1. Okay. Identify the stream. So block B1 is connected with the S1, S2 and S5. Okay. So the question is about the value A. So if you go to this, the value A, so value A, you can see this is the palette for the block B1. So now you need to only focus on block B1. Okay. Then block B1, then it's asking about the pressure. So the block B1 is connected with the stream S1 input stream, S2, S5 output stream. Now you need to go to the results. So here you will see you have the stream results S1, S2, S3. Okay. So the concerned streams for to find out the value of A for this block B1 should be S1, S2, and S5. Now check the data for S1. So S1 is S2 and this is S5. And we have asked about the pressure. So see it very carefully. The pressure in the S1, that is input stream to the block 1, is 2. In S2 and S5 are the outlet stream. They are also having the 2. So it means that uh, the pressure is not changing. Okay, so we can understand two things. So there is no pressure drop because the incoming pressure is 2 and the outgoing pressure is also 2. And other thing, the outgoing is 2. So you can do by in S1, if you enter 0, it means there is no pressure drop. If you enter negative value, then what does it mean?
Is carried under vacuum, sir.
Pressure drop.
Yeah. So if you enter the negative value, that will indicate the pressure drop. So that much pressure drop is there through that particular block. So let me know if I enter the positive value 2, what does that mean?
Means the operating pressure, sir.
Yeah. So if I enter the 2, that means that the this block is operating at this pressure and the outlet will be at this pressure. And if I enter minus 0.02, what is the meaning of that? Then suppose let me know this is the block. Okay, you have one input and you have two outputs. And this is, we know, we have seen it is 2 bar. If I entered here minus 0.2, then what will be the pressure at A and B?
It will still be 2 respectively. 2 bar.
It will still 2.
It's
No, sorry, it
1.8.
will be
1.8.
1.8. 1.8.
Yeah, right. So it will be 1.8. So if you enter a negative value, so this indicate that this block, because whenever you use a block, so if you are saying that it's a no pressure drop, so it's a real, like, in practically there will be slight pressure drop. Okay, so because if you are having some kind of feeling, and also mostly there will be some pressure drops, so maybe it's very less, but still there is chances of pressure drops. Okay, so if you are entering negative value, it means that this block will drop the pressure by 0.2. So inlet 2 bar and outlet will be 1.8. And if you enter only 0, then it means there is no pressure drop considered. And outlet will also be 2. Or if you enter directly 2, it means the outlet pressure will be directly 2. Okay. And just let me know one thing. Suppose if in the same block, okay, if I enter here 4 bar and my inlet stream is at 2 bar, then what will be the pressure at A and B?
4 bar.
Okay. And what is the significance of this? Is it correct to write
It's
like this?
practically impossible, sir.
Yes. So in the Aspen, but what do you think, the Aspen model will run or not?
It will run with warnings.
So error.
With warnings or error?
Error.
Yes, it will
Okay.
show. It will show error.
So like it's just your for assignment, you can say. Just we will have discussion about in the next class. Suppose if you run a system like this, maybe suppose just enter 2 bar and then maybe 2.2, like, because 4 is slightly, maybe 2.2, will it run or not? Just check it and let me know
We
the
need
answer.
to increase the pressure.
So my question is that will model run or not? Will you get the results, or like will you get to know, okay, you made a mistake? The point is that
We can
You-
get the result with error. I think.
yeah, results with the error or warning, please check it. Okay, because sometimes when you are having a very complex flow sheet, so sometimes these kind of situation will be there. So try to simulate this situation with the simple models, and then you will be aware of these kind of situations. Okay, so we'll discuss this. So the next question is, yeah, the missing value indicated by B in figure 8. So this is the figure you can see here. So the B1, it's asking about the value B. So see it carefully.
It's 0, right? There is no change in pressure, so we don't need
So
heat duty.
these are the results.
Zero.
There's no change in temperature, right? So heat
Yeah, so
duty
the
is
correct, yeah, so heat duty is not related to the pressure. Okay, because maybe sometime you can also have same temperature, okay, with change of pressure. You can apply some cooling and all, you can have those things. So the correct way to say is that the temperature, because we are talking about the heat duty. So if there is like the change of heat duty, then either the temperature will increase, okay, so it should increase. If it's like if you are cooling it, then it will decrease. So there is some interaction of heat, either addition or removing. But you can see the temperature is stream S1, S2, and S5, I think. The block
Yes, sir.
is, yeah. So this is the block B1. Again, we need to see the S1, S2, and S5. Okay. So if you have to see the heat duty, then see the results for stream this, this, and this. Okay. So if you see it carefully here, the S1, S2, and S5, the temperature is same. So there is no heat addition. Okay. So the heat duty is 0. So the missing value indicated by A in the figure 9. So this is the figure 9. You can see the missing value A. Just observe the figure carefully. Take 1 minute. Then we will go back to the other figures. Okay, have you seen it?
Yes.
Okay. This is the main figure. Again, you can note down the streams. I think in that question you have seen the block. So you can note down the respective connected streams. So which was the block in that figure?
E4.
B4. So the block was B4. So the connected streams are S2, S3, and S4. Okay, S2, S3, and S4. And now these are the results. Now let me know the answer.
1.
1, sir. 1.
Oh, very quick. 1. I will give you some more time to go through the question again. So the question is, yeah, the missing value indicated by A in the figure 9. You have seen the block, okay, it's a separator, and you have asked about the value A. You have given the component name, you can see it, and these are the results. What was the stream numbers?
S3, sir.
Stream number S3. S3 and
Yes, sir.
no, I think there was a one
S2,
block. So S2, and this one is
Yes, S3
S3.
also.
Okay, so S3
No,
and
the other one
S4.
is S3, the other one is S4.
Okay, mean to say the S2, S3, and S4. That's the main important. Let me check it again. So S2, S3, and S4. Okay. So you have S2, S3, and S4. Okay. So these are the values. Now let me know the answer. We have one answer as 1. Is it correct? Does everybody agree? Because the point of these types of
No,
question is that
S3, it's in the figure, it shows S3 block. So S3 stream. So here the hydrogen value is 44.9862.
okay, so what will be the answer then?
Sir, can you go to the previous slide?
Yeah, so this is the question. So this is the question actually. Please go through the question carefully. Because the
No, sir. It's
purpose of
previous.
which one, which figure? This one?
No, sir. This A is 1, sir.
Okay, so you mean to
Because
say
it
A is
indicates.
1.
It's asking
Does
for the mole.
everybody agree with it? Is everybody agree with it? A is equal to 1.
No.
So it's really okay. So what is your answer then? These are the data.
Yes, it's 1 because it's asking split fraction, right?
Split fraction. Okay.
It cannot be, it is not supposed to be 1 because S2 is the inlet, right? And we can see that hydrogen in the inlet is 0.6. I can see that
Okay.
S3 has 1 complete mole fraction of H2 and S4 also has some of the hydrogen. So
Yes.
it cannot be 1. It has
Yeah,
to be
good
something
observation.
else.
Yes, good observation. Nice. So please go through the question again because it's really important to understand because I know that you can model the things, but the thing is that when you are modeling, you need to also be aware of how to analyze the results. That's a very important thing. Okay? Because
But
the
sir, it is
modeling.
possible now.
Sorry?
Sir, like it is possible because the mole flow rate of the S2 stream is 82 kilomoles per hour. While the molar flow rate of the S3 stream is 44.98 kmol per hour. So it's
Okay.
like complete separation of H2, right? So it is possible. It's not like it's not possible.
Okay. Then what will be the answer? What is your answer?
So I
1.
gave my answer.
Okay, so let's see the answer.
Yes.
The answer will be
Sir, it
here
is
0.85
between
or 0.95. Yeah, we have another answer. Yeah, please.
0.8.
0.8. No. So how are you
Can we
calculating?
wait for?
Yeah.
With
Yeah, we can just wait because it's a very good discussion actually. So let me just go through the question again for all of you. So this is the question, okay? So here you need to tell me. So you have given a outlet stream number as 3. Okay. So this is the stream. You need to find the split fraction. Okay. Understand it carefully. The split fraction. So what is the meaning of the split fraction? First, just let's discuss this. Suppose if you have one stream and it is splitting into 2 streams. Okay. So this is suppose is having a flow rate of X. Okay. Then and this one is having, suppose I'm saying the flow rate of Y. And this one is having the flow rate of 0.6 X. So it means that this flow rate, like the stream A, this stream B. So B is having 0.6 of X. So how will you calculate the split fraction? Then what will be the split fraction of for Y? So what will be the value of Y in terms of X?
0.4x.
Yeah,
4.
it will be 0.4 X. Okay. So then what is the split fraction for stream A? How much the split fraction?
0.4.
Yes. So how will you calculate it? How will you calculate the
We
point
just
4? Suppose you don't know the point 4 because now you have know the point 4. But suppose if you, how will you calculate? Now you don't have this value. You have only this value.
we do y by x and we find the
Yeah.
split
You will do the y by x.
x.
And what is the y? And what is the x?
For our question, y is S3 and x is S2.
No, no. Okay, no. Y
Oh.
is the, like, it's the flow rate or molar ratio. What is that? I am asking in that direction. So it's basically the flow rate.
Flow
Yeah.
rate. Flow
Yeah.
rate.
So it's the molar
Okay.
flow rate of H2 in S2 divided by molar flow rate of hydrogen in S3.
Yes, yes. So whenever you want to calculate the fraction, okay, split fraction. So it's asking about a split fraction of the flow. So the split fraction of, like, the hydrogen of this, the total. Okay, because this stream is splitting into these two streams. Okay, so whenever you want to find out the fraction, then find out based on this respective to this stream. Okay, if you are saying 1, so 1 is the molar concentration of hydrogen in this pipe actually. So this pipe only have hydrogen. That's why you will see the mole concentration. So it will show you the 1 because this pipe only it's showing the composition basically, the molar composition. So the stream S3 will have only hydrogen. So you will see like 1 only. But that's not the split fraction. Now you have this data again. Just calculate again and let me know the answer.
It's 0.899.
Yes. How will you calculate?
$49.9846 divided by 4.99846. It's a
Yes. So
flow rate.
basically the hydrogen concentration in this stream and the hydrogen concentration in this stream, the flow rates,
Yes.
and
Yes.
find out the ratio of those flow rates. Then you will get to know the split fraction. So suppose this stream S2 is having, the S2 is having the hydrogen flow rate is this much. Okay. And this is separating the hydrogen in S3 and you are getting this flow rate. So if you want to know the how much fraction of this hydrogen is transferred to stream S3 and divide it. Okay. And you will get the
0.
Yeah, I think 0.9. You will get the around 0.899 or like that. Okay, so
Yeah.
so that is the answer.
0.9.
So I think some of you were saying the 1. So I think you were looking at this mole fractions. Okay, so be clear.
Yes,
This
sir, I'm
is
wrong.
the meaning that the pipe or the pipe S3 or stream S3 only have hydrogen, nothing else.
Yes.
Okay, so the mole fraction, the composition of this stream is only the hydrogen. The meaning of this is that. Okay.
Okay. Thank you, sir.
Yeah. So be careful with the next questions also. Okay. Other questions are also similar to this. So be careful. Yeah. So the missing value indicated by A in the figure 10. So this is the figure 10. So look it very carefully. It's about the wall B3, block B3.
Can you show the flow sheet?
Yeah. So everybody
Result
have
summary.
seen this clearly. Okay. So this is
Yes.
the I think you also need to see the connections to this wall. So this is the wall and the stream S6 and S7 are under consideration. Okay, S6 and S7. Yeah.
One ATM,
And
sir.
Now what is the answer?
ATM.
One ATM.
One ATM.
ATM, sir.
Okay. Everybody? Everybody agree with one ATM?
We can give it in terms of pressure drop also, na?
So this is the question.
Either -1 or 1, right?
Okay, -1 or 1. Yes, so the 1 is the answer. Regarding -1, I think we can give as a pressure drop also, but please check it like is the wall accept the pressure drop? I think it will accept. Please check it, okay, and let me know. Because here for the pressure drop, we have a different section. Okay, so if you
No,
enter, yeah, negative value, it will not take that, yeah.
So,
Yeah,
so
So in the wall, we need to specify the pressure clearly, okay? So it is not like the other. So because here we have another option for pressure drop. Okay, so be careful with this. So you need to give only one answer, the positive value, okay, the outlet pressure. That is the one. Yeah, so we have another question. I think it's also regarding the class. In class, professor took a case study. So it's regarding to that only. So please open your Aspen and just use the Aspen and let me know the answers. So we have a mixed stream of 500 kilomole per hour methanol, 300 kilomole per hour ethanol, 100 kilomole per hour water at 25 degree and 4 bar pressure. Use NRTL RK property method and find out the boiling point of pure components through calculation of Gibbs free energy. Place the stream at the boiling point of these components at 4 bar. Answer the following 5 questions with accuracy up to 3 digits. The first question is the boiling point of water at 4 bar. Take 2-3 minutes, 5 minutes. Open your Aspen. Define these components, the property method. Everybody, are you doing this?
can we answer?
Yeah, yeah. If you
Yes,
have the
sir.
answer, let me know.
143.686.
Okay, so we have an answer
Yes,
of
sir. It's around
43.686. Okay, so
143.68.
okay, nice. So just let's start with the solution, because I think next 4 questions are dependent on this only. So we can also model in this class. Let me share my screen. Yeah, please tell me the components.
Methanol, water.
Methanol, ethanol, water.
Methanol. So first, when you define the components, okay, I think I did a spelling mistake here. Okay. So methanol, ethanol, and water. So first define your components, then next, then the method. You have given a method in NRTL RK. What is the method?
NRTL-RK.
ENRD.
NRTL RK. Okay. NRTL RK, right?
Yes, NRTL-RK.
Then go to the next, then again next, then run the property analysis. So results are available for the property analysis. Okay, you can go to the simulation window. Yeah, then what is the given in the question?
We have to find the boiling point of water at 4 bar pressure using pure
Yeah.
component. This gives free energy.
So which kind of block we will use here?
We won't use a block, right? We will go to properties directly, and we can use the pure component analysis.
Okay. So maybe the other questions are connected to the blocks. Okay, we can also go to the properties. Okay, and then we will go to the pure. So if you want to use those things for your complete flow sheet, then you need to use the blocks and all. But before that, you want to find out the properties data, okay, regarding the boiling point and all. So be in the property, then here you can see some analysis tools, pure binary mixture, solidity, PT envelope and all. Okay, so in this we have asked about the boiling points, and we have given use the Gibbs free energy method, right?
Yes.
Yeah, so go to the pure analysis, then method is selected, property thermodynamic, and the properties. Which one is the Gibbs free? G, I think.
G.
Okay. Okay, so property G, free energy for a pure component. You can see there are multiple properties. To take your cursor to that particular, you can see the name. So like DS is the entropy departure for a pure component. Okay, like this. Then suppose we need to see for the methanol, select the component. Okay, and anything else you have to do?
For 4 bar pressure.
Okay, so we have given the pressure 4 bar. So by default it's 1.01325 bar, but we have given 4 bar. Select 4. Okay.
It's
And
for
here you can
water, sir.
select the, sorry. So the first question was for water.
Question is
Okay.
asked for water.
Water. Okay, so for the water, you also, so
We
question
have
is
to
asked for
select
the
vapor
water.
also. Phase
Yeah.
vapor too.
Yeah, you need to select the vapor phase also. Okay. Liquid
Can you
vapor is
show
selected. Then the point, the end point you can increase. it's only the 100. Make it 150. You can change the intervals also. Okay. And run. Okay. So 150 is, it's here, around here. So you can see. So now those who were saying the answer, so what is your reasoning behind the answer? How can you interpret, like, okay, this is the boiling point? Please tell me.
We change the start point and the end point to such a degree that we can get the accurate results.
Okay,
Uh,
okay, so okay, I know that, but like this graph
Intersection
is
of the vapor phase
okay.
gives energy and
Yeah.
liquid phase gives energy. The point at
okay, yes.
which it intersects is it.
So you can see we have so there are two lines, the blue and the green. So the green is the liquid gives free energy, okay, and the blue is for the vapor. And the intersection of this gives free energy will give you the boiling point. Okay. So you
Can you
can
show
see
the
here.
question?
Yeah.
So can you show me the question?
Yeah, just a moment. So the boiling point of water at 4 bar. Okay. So here we can see. So you can also change the range. So you can only select from 130 to 150 to a more close-up look at this. Or you can see, like, use the tracker also. You can find the point. The answer we have is how much? 143.6 or 7. Okay. So let's go to the next question. The boiling point of methanol at 4 bar. So just note it down, the previous boiling point, because we will need that further. Now the boiling point of methanol.
(104°C).
So we have one answer quickly. So just wait for 1 more minute, and after that we will go through the model. We have one answer. How much? 1.
104.
Okay. And what was the due date for assignment 6? I think the assignment 6 have already completed. What was the due date? Anybody?
Let me check.
I think it's over now.
7th.
Assignment 7.
It is over.
Yeah, it's
Sixth,
over. Okay.
sixth, right?
Okay. Basically, it's over, right?
Sixth assignment, right?
Yeah, assignment 6. Yeah.
Sixth is over.
Yes,
Okay.
sir. It's due date says gone.
Okay. I received a query regarding that assignment, a question. So we will go through that also. So I received some queries regarding that. So at the end of this class, we will go through that particular question. So is the answer correct, everybody? Are you getting 104?
Yes, I am getting 104.17.
Okay. So the correct answer is 104.02 to 104.2. Okay. So you can do as we did for the water, just select the next component. Okay. Choose the temperature, change the pressure, and do it. The boiling point of ethanol at 4 bar. Now change the component to ethanol and let me know the answer.
Hundred and 17.85.
So we have one answer 117.
Yes, 117.88. Sorry.
Okay, so yeah, we have one answer. Just wait for 1 more minute for other answers. Let's see.
Yes, sir. 117.87.
Okay. So answer is 117.87 or 85. It is in the range, so it's okay. Okay. So now the K value at the boiling point of ethanol at 4 bar is. Now you have to find out the K value at the boiling
Yes.
point of ethanol. And the ethanol boiling point is how much? 117.85. Okay, consider this boiling point and find the K value.
We see the question once. Thank you.
So with the property analysis, you know the boiling points. Now the question is asking about the K value. So it's given here. You can see the place the stream at the boiling point of these components at 4 bar. You've given the flow rates and all. Go to the simulation environment.
What do we have to find? The K value of
You have to find the K value of
ethanol.
the K value at the boiling point of ethanol at 4 bar.
We have to find the K value of ethanol at the boiling point of ethanol, right?
K value, yeah.
Of the answer.
Ethanol, this boiling point, this pressure.
1.057.
It is supposed to be 1, right?
So we have one answer. How much?
1.057.
1.057.
Okay, so we have an answer. 1.057. Everybody, are you trying or you also have this answer? Okay, let's go to the Aspen window. So those who have solved, let me know how should I approach. Okay, so yeah,
We'll go to the separator. We'll add flash
so
3.
I think two or three of like you have answered. So one by one, just first one person let me where I should go, then the next person will give me the next step, and like this. Okay, one by one. Okay, so so then we go to the simulation. Okay, the next.
We'll go to the separator.
Yeah, why separators? What is the reason for this?
Because we need a flashing column.
Okay, because it's mentioned in the question also that you need to flash it. So we need to select the flash column, then it's in the separator. Okay. Next. So we need to select, we need to add the streams. Okay. Material streams. Next.
We'll click on next. It will take us to the feed input. We'll input the feed.
So let me know the feed inputs.
It is 25 degrees Celsius, 4 bar pressure.
25. So here you need to enter the inputs. Okay, for this, for the streams. The stream, you can see the name here S1. The temperature is 25, pressure 4 bar. Okay.
And we have the flows of methanol, ethanol, water.
Yeah, flow rate.
500 for methanol, 300 for ethanol, and 100 for water.
Is it correct? 500, 300, and 100.
Okay. Next.
So be careful. It should be the mole flow and check the unit. Okay. Then anything else?
No, we have sufficient input data.
Yeah. So when you have sufficient inputs, you can see this blue tick. Okay. The white circle and the blue circle and the white tick. Now if you click on the next, then you will go to the block B1. Yeah.
Yeah. We'll input the temperature of ethanol, that is 117.85.
So here we need to input this temperature because what is the reason for this? Because specifically we have asked about, you have to place the input stream at this particular temperature and this particular pressure. Right?
Yes.
So it's input. Do we need to add anything else?
No, sufficient data. We have sufficient data. We don't have.
Okay. So run it. Yeah. So now let me know where will you check the K values.
We'll go to the block B1 results.
So here you on the left side you can see there the blocks and the everything in this window. You can see all the inputs and all. So here you can see the block B1. You can see inputs, dynamic, block options, results. So here the results. Yeah. Then
we go to phase equilibrium.
So here you can see the summary. Okay, in summary you can see the outlet temperature, outlet pressure, vapor fraction, and all. Then there is a balance. Okay, here you can see the balance, and the phase equilibrium is here. So here you can see the K values. The K value for methanol, ethanol, and water is here, right? So
Yes.
let's go to our question. Thank you for your help. So the K value at the boiling point of ethanol at 4 bar is, it's 1.02 to 1.08, and the answer is 1. Yeah. So it asks about the ethanol. So ethanol is 1.05. Okay. So it's 1.02 to 1.08. So this is the correct answer. So now the question is, the mixture will form azeotrophs within the above temperature range of boiling points. True, false? So it's asking about the azeotrophs, okay? And you have given, this is the question, okay? So just place the stream at each boiling point that we just found for the ethanol, methanol, and water. And let me know, is there any chance of azeotroph? True, false? The boiling point, you just note down the boiling points. For the boiling point of water is 143.6. The boiling point of methanol is 104. And boiling point of ethanol is 117.85. So now you have all three boiling points. Just do the same, like find the K values and all, and let me know, is this true or not? The mixture will form an azeotrope within the above temperature range, like of the boiling points. How will you check it? First, the question is that how will you check it?
Can't we use the azeotrope search method?
Azeotrope?
Search method.
Okay, yeah, try that. And what is the meaning of azeotrope? Actually, I'm not from the chemical engineering background, so let me know a comprehensive meaning of azeotrope, so I can also increase my knowledge about azeotropes.
Azeotrope is when a mixture is formed and there's a certain temperature at which the boiling point is same for them. If you boil the mixture, you'll get the same components in the vapor phase in the same mole fraction.
Yeah, right. So basically, if you want to see that the mixture will form an azeotrope or not, then how should we check it? I think for the boiling points. Because if the boiling points, you know all the three boiling points, and maybe then you can use the PT envelope directly to for the all these three components, okay? And you can draw the PT envelope and you can see, is there any intersection of the PT envelope for the boiling points for these three components in this temperature range. Just try this, or maybe you can also try the azeotrope method I think you were telling. So just take 2-3 minutes. I also given you a hint. So let me know the answer.
There is an azeotrope.
Sorry?
There is an azeotrope. I can see it.
Okay, there is an azeotrope.
Yeah.
Okay, at what temperature?
117.497.
Okay, and
It's in
which components are taking part?
ethanol and water.
Ethanol and water. Okay, so we have one answer. So then you are saying that this statement is true.
Yeah, it is true.
Okay, and how did you check it?
Well,
Is forming.
I went to simulation. I went into analysis. We have tool known as Azeotrope search. I went into the input. I clicked on the three components, and then I ran the simulation, and I found out the result.
Okay. Anybody, are you still trying? Should I wait or should I go to the answer?
I am checking with the PT envelope. Can you wait?
Yeah, just check it with that. Yeah. So take 2 minutes more and check with the PT envelope also. Anybody? Do I have any answer from you? Anybody still trying? Let me know just quickly. Are you trying? The mixture will form azeotrope within the above temperature range of boiling points. True, false? What is the answer?
I got true, but not getting the verification by PT envelope.
Okay, so it's false. So go through the PT envelope. Okay, and look into this. So let's go to the PT envelope. What is the flow rate for methanol?
500. Ethanol 300.
And water?
100.
So can you do all three component in one PT envelope? Can we do like this? Let's see. Okay. So in this way, you can see the PTNL, but it's better to make, I think, different, okay, for each component, and we think the pressure is 4 bar, okay, vapor liquid, you can check it. The temperature range that we have given in the question is the boiling points. Okay, so if you also look into the something is I'm making a mistake. Anybody, do you know
It
where I'm
is
making a
showing
mistake?
it is showing a warning. I'm getting the same thing. I'm getting the same graph as well.
Just try with the each actually. Okay.
Okay.
So if we first draw for the methanol, so we have a graph, the same units. Okay. Then again draw a new one. For ethanol, how much the flow rate?
300.
300.
Okay. Yeah. So okay, we need to make the axis same. Yeah. So just draw a different flow rates. Okay, then you will get to know it. So if you draw one more graph, so this one is like one is we have drawn for what? I think we have drawn for two inputs.
Methanol and ethanol.
Yeah. So please draw one more and merge those all and see. So you will look into this that they are not matching at particular pressure and temperature. They will always, there is always gap. Because when you are already, when we enter the all flow rate in a same PT envelope, then it means that that is you are analyzing a mixture, not a different. Okay, so the question is asking about, suppose you have three different, then you are mixing it like that actually, not a, I think maybe I'm not getting the exact point in the chemical, like what, but if you see through this actually, so we need to do it like separate, and if we enter all the flow rate in a same, then I think I need to check it, what will be the reason for that, why they were merging. So I will check it and let you know. But I think I'm just assuming that if we are entering the same values one at a time, like at a single time, then it's taking a complete mixture. Anybody, are you aware of it? Why we were having the complete overlap of the graphs when we were using the same values? Okay, so I think that is the reason, or we will look into this. But if you, anybody have all three graphs? So we can draw one more. So what is the flow for water?
100.
100.
100.
Yeah.
Yeah. So with single y-axis, you can see, but we have to look
They
into
say at
here.
the top of ethanol and water.
Yeah. So at this, yeah, it's possible. I think, yeah, they are merging here. Right? But the answer is saying the
Yes, sir.
false.
My
So
graph of PT envelope is not merging with any. I have three separate
okay,
graphs.
your graph are not
I guess
merging.
it's
Yeah, my graphs are not merging.
So why my graphs are merging? I think something is with the overlapping, I think.
I think it's going closer, but it is not merging once you
Yeah,
zoom it fully.
yeah, it is very close, but it is not merging. It is very close.
Okay. So if you change the scale, then you will look into it. Okay, I think because I'm not able to see all the graphs together in my software. I don't know why one is. I think last time also I was having this. I think I need to update my software. So if I see this one, then I'm not able to see these two. This PT V2 is not visible. Okay, so they are not merging. Okay, so they are not merging, so it's false. Okay, so mixture will not form an azeotrope within the above temperature range.
Can we look at the azeotrope search method in the simulation as well? Because I'm still getting that there is an azeotrope of ethanol and water.
Okay, let's go to that.
Yes, sir. Me too.
Okay, so if we go to the, where is that method? Azeotrope?
We go to simulation.
Yeah. Azeotrope search, yeah.
Yeah.
So if we select these three, then the temperature, the pressure is how much? 4 bar.
4 bar, yeah.
NRTL RK, vapor liquid. Okay, report unit temperature, okay, and report. So investigate for azeotrope at a pressure of 4 bar. So we have at azeotrope. Yeah. The temperature is 117.50. Okay.
Yes.
But what is mentioned in the question?
Sir,
Okay,
it is,
boiling points.
yeah, it is between 104 and 143.689.
Okay, so actually I'm also not an expert of these azeotrope and things. So yeah, with the report we can see it, but with the PTNLF we cannot see. Okay, so just raise a query. Okay, just raise a query. We will look into it. I will discuss with my colleagues. I'm not from the chemical background, so I'm not fully expert of these things, like why they are showing here and not there. Okay.
Thank you. Thank you.
Yeah, but maybe in next class we can discuss it. But it's a good observation. So here we can see, but the temperature is 117.50, maybe because the boiling point is okay, but still it's in this temperature range. So just one of you told me that azeotrope, when the vapor phase, okay, in the vapor phase they will be in the same state, right? Am I right?
It
Yes, sir.
can be a vapor. It can be liquid and
Okay, it can be liquid and vapor also, both.
yeah. Because in
Okay.
QT and wave we get a figure wherein we cannot discriminate between the liquid phase and the vapor phase at that particular temperature.
I think the question is asking because I'm just making a probable guess, okay? Because the question is asked mentioned about the boiling points. Okay, so first we need to be aware that we were only like after boiling points we are observing. So
Yes.
if you look carefully, then the
Uh,
temperature for is like 117.50. So if we look at this temperature, then ethanol is not in the vapor phase. Ethanol will be in the liquid phase because the
but
temperature of boiling point is 117.87. So
yes.
at the boiling point or above boiling point, they are not an azeotrope.
Hmm. Yes.
Okay, so I think it's just I'm not from chemical background, but I'm just assuming through this data analysis that because they mentioned about the boiling points and you see the boiling points, okay? So at this temperature, only water, like only methanol will exist, okay? So at this temperature,
Yes.
ethanol is not there, the water is not there. So they will not form a azeotrope in the vapor phase.
Hmm.
So
Yes.
yeah, so look into this. I think this is the answer, but you can also verify it. And just if you have still doubt, please raise a query. Okay,
Okay.
okay.
But
It's a
this is a
discussion
constant
actually.
boiling.
Sorry.
This is a constant boiling azeotrope, na? So we, the boiling point of water is reduced from 143 to 117. Na?
Actually, I'm not expert, but I'm just assuming a guess. So yeah, maybe I don't know the exact answer. Okay, so it will just raise a query. If you still have doubt, I'm just assuming through this actually. I'm not expert of this, but maybe with the mixture, I don't know. So just check it, just raise a query, we will look into it. Okay. But
Okay.
from the NPTEL team, I am having an answer of false. So we have to look into it. Okay. Let's move further. So Aspen Plus has a specific model block with underlying equations of membrane-based separation. Do we have a membrane-based separation model?
False. Then
False. Why? What kind
we
of separation models we have in Aspen?
we have basic separation models wherein we separate on the basis of flashing or split fraction.
Yeah. So we don't have a particular model to separate based on like membrane or how they behave. If you have some, if you are working with a membrane and you know the mathematical equation and all, you can write your own code and you can make your own block, okay, and you can use that. But in the Aspen, we don't have already built-in specific block for separation using membrane-based methods, okay. So based on the ratio of relative volatility, select the components in the order of most volatile to least volatile. I think it's from the case study
We
that we took in the class. How will you find the volatility? I think from the K values.
It's the most volatile followed by xylene.
It is benzene, toluene, xylene. Yeah, it is the B
Benzene,
option.
Option D.
option D, benzene, toluene, and xylene.
Yeah.
So yeah, option D is correct. Benzene, toluene, and xylene. So for more detail, you can refer to the class notes. The Fensk equation is used to calculate the minimum number of stages required while using DSTW model. True, false?
Yeah, true.
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 True, true.
So it's true. Okay. Which among the following are relevant base methods if petchem method filter is chosen in property method and options? Just open the Aspen, use the petchem method filter and see what kind of property methods you can see there.
Chow Cedar.
Okay, there's two, Chow C and Wilson.
Cedar and Wilson. Yes.
Yeah. So basically you can use a method filter. Okay, so based on that, you will see only the relevant methods. Okay. So in Aspen, you can use this method filter option also. So we have another question. Look it very carefully. Just take 2 minutes. Understand this. So we have block B2 stream input S1, S2, and S3. Then on the right side in figure 2, we have some options like A, B, C, D, and F, G. You can see the components. You can look it carefully. Okay. Should I move forward?
Yes.
Okay, so I think you have seen the picture. Then we have this picture also. We will come back to this picture again. So the question is, stop sharing. Just a moment. I think, yeah. Okay, the figure 1 is relevant portion of main flow sheet of Aspen. It's not visible. Just a moment. Yeah. So figure 1 is the relevant portion. Is it visible to you?
Yeah, we can see the question.
Yeah, okay.
Log.
Okay. So the main flow sheet of an Aspen Plus simulation figure 2 is the data input palette, which upon completion and simulation run yields the results as indicated in figure 3. The next 6 questions are based on the figure 1 to 3. So the block B2 is the question number 1. So these are the results. You can look at the results. Okay. These are the figures 1. The block, what is the block B2?
So it's a flash key.
Flash 2.
Okay, so you can see the the schematic, then the model palette for input parameters. Then you can see the results. Based on the results also, you can see what kind of block B2 is. So we have one option, one answer. What is that? Flash 2.
Yeah, flash 2.
And what is the reasoning behind this?
Sir, in your simulation, when you click on flash 2, you drop down, you get a similar figure.
Okay, it's not a good way to say it. Okay, okay,
Yeah,
you
in the
can
in the
say.
tab near to flow sheet, we can see.
So
We can see that it has
in the tab also you can see the flash 2, but it's I'm not fully agree. Just suppose if I crop the picture, then you will not able to see the tabs, no?
we can see
So
that it has two outputs.
yeah,
So
one
we
thing,
can
yeah, nice, good. So you can see
distinguish
two
between
outputs.
flash 3
And
and
what kind of information you can get from this? I think you should also use this one. Because okay, you can see the here actually you can see suppose if the picture is cropped, then you will not able to see this flash 2 option. Okay, then you need to answer it. Then you can see okay, we are doing something like one input stream to output stream. Okay, we have these kind of inputs. Okay, then you have also this picture. Suppose it's also cropped, you cannot see this the top options. You cannot see this plus 2. Then you need to see the results. So based on that, you need to identify. That's the question. So here you can see the phases actually, vapor phase and liquid phase. Then you can see, okay, so vapor phase and liquid phase, it can be the flash, okay, and how is separating. So based on this, I think it's the best way to identify a component. Okay, so to the all the results and all the basic inputs. Maybe sometime in this case it's given, but maybe suppose picture is cropped from here, then use this data also. See it, look at carefully, and then answer. Okay, so I'm just adding to the this actually. The block B2 is the flash 2. Okay, the temperature input 8H in figure 2. So let's go to the figure 2. So this is the figure 2. Here you can see the temperature H. Okay, so it's asking the mixed temperature H. Let's go to the this one.
318.15 Kelvin.
See
318.
the question. The temperature input at H in figure 2. Okay, this is the figure 2. Okay, just observe it carefully. Then I will go to the result section. Take 30 seconds to observe it. Now let me know the answer. I have one answer 318.15 Kelvin.
45.
Yeah, now you have correct answer. Okay, because it's really important because in the results you can see the answer in the kelvins, but here it asks about in the degree centigrade. Okay,
Celsius.
yeah. So just don't say directly. Let's go through the question first. So the answer will be 45. The pressure input 8J in figure 2. So where is that J? Yeah. So the J pressure input. Look at it. Take 30 seconds. Okay. So yeah, let me know the answer.
1.
One. How?
Because the input there was in ATM and we have the answer here in bar. We can see that S2 and S3 is 1 point, the pressure of the outlets are 1.01325 bar and 1 ATM is equal to 1.01325 bar.
Yeah, nice. Good. So be careful with the units. Okay. It's one. The flow rate at K in figure 2, the flow rate input at K. So the K is this one, the flow rate input, okay? And these are the results.
$100.
So yeah, so it's about the mixed stream, okay? The total flow rate, because here you can see we are entering in the mole fraction, the total flow rate is kilomole per hour. You can see the mole flow, it's 100. The mole fraction input at D. Okay, the mole fraction input at D. So this is the D. Okay, look at it. So D is the propane. Now let me know the answer.
Can we go back once again? Thank you.
So they are asking about the mole fraction for point D.
Yeah, we can go to the result. Please. It's 0.1.
Yeah, point
Yeah,
point
0.1.
1. Yeah, because this is the mixed stream S1. You can see the mole fractions of H2, methane, ethane, and everything. Okay, so its propane is 0.1. The mole fraction input at E. So E is the hexane, and hexane you can see here, it's also 0.1.
0.1.
So both are similar question. We can skip that. Okay. So this question is important. I think, yeah, this one was in your assignment, week 6. I think most of you have already submitted it, or maybe you will have you have right answer and you solved it correctly. But do you have all answer for this, everyone? Because I received some queries regarding this question, regarding the optimization. Are you able to
Yeah.
do the optimization?
Yes, it falls.
No.
No? Yes? Anybody?
No.
Okay. So we have one answer, no. Okay, so we quickly go through this. Okay. So just let me share my screen. So I think everybody, are you aware of the question? Or should I read the question again? I think because it's from your assignment, so I think it's known to everybody. But okay, so let's just quickly. So the two streams of water are poured in a tank. So we have two streams of water. Choose the best method as stream NBS. You have given a method. The first stream is following at this flow rate. Okay, temperature given, pressure given, and the other 8 flow rate, temperature given. So you have given everything, just follow that steps only, those steps only. The outlet stream from the tank 1 is then passed through the pump, having a discharge pressure of 14 atmosphere, suction area of 600 square mm. Then the tank pump and dry efficiencies you have given. The water is then transported to another tank via a 500-meter long pipe. You have given the the material carbon steel, schedule number 40, okay, having 2 gate walls, 4 butterfly walls, 12 large 90-degree elbow, and 20 straight tees. The temperature profile is linear inside the pipe with the outlet temperature. The pipe connection type is flange welded. The pipe rise is 0.2. A single fluid phase is assumed prevailing inside the pipe. Okay, you have to change the iteration and all. The flash option to a 60. Change the default convergence method to complex. You've given the way. Go to the convergence options, defaults, and default method. Write a Fortran code. So I received query regarding this Fortran code actually. So I think these things you can do. Everybody, are you able to do up to here, or are you only facing the issue with the Fortran code? What was your difficulty in this question? Just let me know quickly.
Fortran code. Yes,
Okay.
Fortran.
So I think most of you are able to do up to here. Only thing was the Fortran code. Okay. So just we will focus on to this Fortran code only then. So write a Fortran code and find the optimum diameter d for which the given objective function will be minimum. So you have given a function f equal to 1000 d plus 10 raised to power 17 by d raised to power 5. We're varying the inner diameter to 50 to 300 with a step size of 0.5 mm. So in the Fortran, you need to be very careful with the how to write the code actually. Okay, because Fortran is a language, so each language have their own operators, like the arithmetic operations. They have some symbols, the operators. So you have to use that actually. Okay, so you can not directly, maybe sometime the plus or minus the multiplication we can use, but for this like 10 to power 17, there are different kind of operators. So just Google it. Okay, I will show you. So yeah. So this way you can model your system. Okay. So just quickly, I'm going it through quickly.
I have one more doubt.
Yeah,
They
yeah,
are
please.
asking for product flow rate, right? But they didn't give any temperature and pressure of the feed. So how we can calculate the flow rate of the product stream?
So
So
which one you are asking about this question?
the yes, this question.
They have given now the first stream
Uh,
they have given, I think. Yeah.
no, in the first part. Sorry, not in the not in this part.
Okay.
In the first
I
part of the
actually
question.
I don't have all the, so just somebody shared me this part only.
Okay,
So
okay.
that's why I'm only sharing this one actually. Okay. So normally I don't discuss the assignment question, but I received like a mail regarding, so they were having issue with the Fortran code. So I thought it's better to discuss in the class also, because maybe some of you also having issue with the Fortran code.
Yes, we are also. I'm
Yeah,
also,
yeah.
but there is one.
So you
Thank you.
can just define the water, okay, as usual. Then go to the simulation, the method you can select it. Just because we have to mix stream, then use a mixture, then use a pump, then use a pipe. Okay. If you go to the pump, then we have given some options. Nothing, I think it's okay. To go to the block B2. So for the pump, you have given the discharge pressure, 14 atmosphere you have given in the question. Then the pump efficiency you have given, enter those. In the calculation, you have given the suction area, enter the suction area, okay. In the flash option, okay. Then if you go to the block B4, so you have given the fluid flow, the pipe length you have given, use the pipe schedules, the carbon steel 40, you have to enter these all things, okay. Then the specification, they have given the linear temperature profile, 20 degree. Fittings, they have given the flanged welded. Just follow the question actually, okay. So normally we don't use these options, but because it's mentioned in the question that you need to use the fittings and all, so you need to give these inputs, then only you will get the correct answer, okay. So fittings, they have mentioned 2 gate walls, 4 butterfly walls, okay. Just enter all these things in fittings, 2, none. So here valid phase is liquid only, it's given. Because the profile is linear also, you can see we are dealing with the water. The profile is linear at 20 degrees, so it will remain water only. So you need to select the valid phase liquid only. Then they mentioned change the iteration to 60. So change it 60. Okay. Then about the convergence. So if you go to the convergence, then the I think options, then the default. So here the optimization method they have asked to change it. So earlier I think it was SQP. Now make it complex. Okay. Now let's go to the optimization. So based on that, you can find the results of some the question they ask, you can find the results. But now about the optimization, that's the main query. How to write this code in the Fortran and how to do the optimization. So how to find the optimum diameter and what is the minimum value of the objective function. So these two questions I'm taking here. So if you go to the optimization, then go to the optimization, then here you will define a new, okay, so let's say O1. And if you go to the O1, then it will ask you input. So let's say select a variable, name it D, and then it will be a block variable. Okay. Then the block, which block? The block B4, the pipe. Okay. Then the variable is the diameter. You can search the inner diameter variable. It will be the in time variable. Okay. Units. Okay. Go to the objectives. Then object. Then you have to minimize. Then select a function. Let's say it's F. Okay, as given in the question. Okay, that's why I took only F. Okay, so let's say it is F, then go to the vary, then again we need to vary a variable b4 from 250 to 300. Okay, step size 0.5 mm, then the Fortran code. So Fortran code, we know we need to enter after column 7. So the code is, this is the code. So here we have 1000 multiplied by D. So in the Fortran, 1000 for the multiplication, use star. Okay, so asterisk, so 1000 star D, then plus, then for 10 to power 7, just use 2 stars. Okay, 10 star star 17, then the bracket, divide, D raised to power 5 means again 2 stars. So this is the operator for exponential operator is 2 stars. Okay, in the Fortran. So you need to use this code. Okay, then if you run it, you will get the results. So like these are the results. So the objective function value is this. Then the value, the final value D is the 282.267. So this is the way you can use this. So the point is that the Fortran code. So if you are not aware of the code, then you should Google it. You should try to find the exact operator or symbol, because if you use directly like this symbol that normally use this symbol, okay, then you will get some warnings and errors that it is not running like that. So you can, I think you also received those errors. So just change it with the star star and you will get the result. So is it clear?
Yes.
Okay. So I don't know the what were the other questions, but I think it's mentioned everything. So I think one of you were asking about the flow rates, so I'm not getting your point. So you can email me if you
In professor video it mentioned,
in.
but not professor's video. The
Okay.
temperature and pressure, the same problem. The temperature and pressure was mentioned, but in the assignment it's not mentioned.
Okay, maybe then they are asking that refer the video. I think they mentioned like that, or I think then they mentioned it that refer to the class video. I think I don't know.
They didn't mention.
I
They didn't mention. Oh, sorry.
or
Okay.
maybe you can, if you still have some doubts, you can email me. No issue. I will look into that. So I think this question is clear to everyone. If you still
Yeah,
have
now
doubt,
it's clear.
so if you still have doubts, so you can email me. Okay. So the so initially, if you see this question is very long, so don't afraid. Just follow the steps. Okay. So like just first use a mixer only. Put these two stream, then run it. Then put the wall, then run it. Then put the pipe, then run it. Like that only. Just follow the steps, and at the end use this objective function. Okay, I think it's enough for today's class. So okay, everybody, thank you for joining.
Thank you. Thank you, sir. Thank you.
So thank you then. Anybody is having any doubt? Let me know quickly. Okay. Okay. Enjoy. Bye bye. See you. So we will meet in next meeting. Okay. Bye bye.
Bye. Thank
Bye.
you.
Thank you.
Thank you. Thank you.